That Java happens before guarantee is a set of restrictions on instruction reordering to avoid instruction reordering breaking the Java visibility guarantees. By the way, I assume you are somewhat familiar with the basics of the Java memory model already, more specifically the thread stacks and the heap and how Java threads use these two. If not, I would recommend that you watch my video introduction to the Java memory model. I have included a link to that video in the description below this video. CPUs can execute multiple instructions in parallel, provided that these instructions are independent of each other. And if you look at the example here on the left, I have shown you an example where the instructions are not independent from each other. You can see the second instruction uses A, which is the result of the first instruction. So these two instructions cannot be executed in parallel. And the same is true in the second set of instructions here, where the second instruction here uses F, which is the result of the first instruction. So these two instructions can also not be executed in parallel. But these two could be executed in parallel, right? Because F equals G plus H does not depend on anything from the instruction D equals A plus E. In order to increase parallelism, a CPU may look ahead at future instructions to see if any of them can be executed in parallel with the one that it is currently executing. So if you look at the example here, you can see if it starts by executing this instruction here, it realizes it cannot start this instruction because this depends on the output of the first instruction. But then it gets to the third one and realizes this instruction here does not use any of the results from the two first instructions here. So this instruction could be executed in parallel with the first instruction. And thus, even if the instructions are listed in this exact order in the program, they may get executed out of order because the CPU looks ahead at future instructions in order to find instructions that can be executed in parallel without breaking the semantics of the program. To make the CPU's job easier, the Java compiler and the Java virtual machine may reorder instructions already at compile time. And that means either when your Java program is compiled into bytecode or when the bytecode is compiled into assembly language instructions by the Java VM's JIT compiler. In this example here, you can see that the original order of the instructions as shown here on the left has been changed over here on the right. The Java compiler has detected that these instructions here can be executed in parallel and that they are independent of each other, and therefore instead of having the instruction executed here, it has been moved up here. So now these two instructions can easily be executed in parallel by the CPU. And the same is now true of the second set of instructions here. This instruction can be executed in parallel with the last instruction here. And so now the execution job has been made easier for the CPU. It does not have to look ahead in the instruction pipeline here to find an instruction it can execute in parallel with the other one here. And that again makes the execution of the whole program faster. Unfortunately, instruction reordering may affect the correctness of multi-threaded applications where the threads need to communicate via shared objects. Throughout the rest of this video, we will look at how instruction reordering may affect correctness of such multi-threaded applications and what the Java happens before guarantee does to fix that. Imagine an application that has two threads running on separate CPUs, and where thread 1 produces frames to be drawn on the screen, and thread 2 consumes these threads and draws them on the screen. The two threads communicate through a shared instance of this frame exchanger class, which I have shown here in the middle. Thread 1 will continuously call store frame, and thread 2 will continuously call take frame. Now, the implementation here is not very well designed, but that is on purpose. That is in order to be able to illustrate some of the problems which the Java happens before guarantee will eventually help us solve. The shared frame exchanger instance is stored in main memory, but during execution, the two threads make copies of the fields of the frame exchanger instance, and these copies are stored in local CPU registers and caches here. And to illustrate that, I have moved the code of the frame exchanger out under the threads here in both sides. Just keep in mind that even if not explicitly illustrated here, even if it looks like there are two copies of the frame exchanger class here, there is actually only one, and it is stored here in main memory. As explained earlier, the intention is that thread 1 calls store frame, providing a frame as parameter to the store frame method, and this frame then gets stored internally in the shared frame exchanger instance. And thread 2 then calls take frame and takes this newly produced frame and draws it on the screen. However, since neither of these fields here are declared volatile, and because neither store frame or take frame contains any synchronized blocks, there is no guarantee that the changes made to these fields in the frame exchanger here, in the local copies of the frame exchanger fields, are visible to the other thread. In order to be visible, two things has to happen. First of all, the thread here that makes changes to the local copies of these fields must flush these updates to main memory. Second, the other thread that reads these fields must read them from main memory. It is not enough that it just uses its local copies here, because then even if thread 1 here flushes the changes to these fields to main memory, if thread 2 never reads them again from main memory and only uses its private copies here, its local copies, then the changes made by thread 1 will not be visible to thread 2. So this implementation here has a visibility problem. If you check out the description below this video, you will find a link to my Java memory model video, which explains this visibility problem in more detail. To fix the visibility problem, we can declare the fields volatile. As you can see, I have done that in the code here, inserted the Java volatile keyword here. And when a field is volatile, that means that every write to the field will be flushed directly to main memory. The values set will be written directly to main memory. And similarly, whenever a volatile field is read, the value of the field is read directly from main memory. This way, the changes written to these fields by one thread will be visible in main memory and will be read by the thread reading the same fields, because they are read directly from main memory. Because of the Java volatile visibility guarantee, it is actually not necessary to declare all of the fields here volatile. The volatile visibility guarantee says that at the time you write to a volatile variable, and that value is written directly to main memory, all the variables that are visible to the thread writing to the volatile variable will also get flushed to main memory. So in this case here, you can see that only hasNewFrame is declared volatile. And inside of store frame, we first write to this .frame, and then this .frame stored count, and then to this .hasNewFrame. And at this time, here, at this point in time, all of these fields are flushed to main memory, not just the volatile field. Actually, all of these are flushed as well. The Java volatile visibility guarantee also says that at the time you read a volatile variable, the values of all variables visible to the thread reading the volatile variable will also get refreshed from main memory. So if you look at take frame over here, as you can see, we are reading hasNewFrame inside of a while loop. And because of that, that means that for each loop in here, we are reading hasNewFrame from main memory, and at that time we also refresh frame stored count and also frame. Down here at the bottom, you can see that we are writing again to hasNewFrame, and because hasNewFrame is volatile, that means that all of the changed variables here, all the variables will get flushed again to main memory. And it is only required that the fields that have actually changed are flushed back to main memory. You do not need to change or to flush a field that has not been changed. I mean, why would you need to do that? So in this case, we know only frames taken count has changed and has new frame has changed. So these two are guaranteed to be flushed back to main memory. Now that we have a visibility guarantee of has new frame, and these are the variables here, we are certain that thread 2 will not spin in this while loop forever. Eventually, thread 1 will change the value of has new frame to true in the store frame method, and this while loop here will exit, and thread 2 will see the frame and take the frame that was set by thread 1 and return that from take frame. To CPU 1, the instructions inside of store frame look like they are independent of each other, right? None of these variables depend on, none of these instructions here depend on the result of any of the other instructions. And that means that to CPU 1, it looks like it is allowed to reorder the instructions inside of store frame. However, if we do that, this might affect the visibility guarantee of the method. Let's look at what happens if the CPU reordered the instructions so they were executed in this order. Now the write to the volatile variable happens at the beginning of the method, and that means that at this point in time, the value of has new frame is flushed to main memory along with whatever is stored in the other variables or the other fields here at that time. And that means that the two subsequent writes to frame and frame stored count are not guaranteed to be written to main memory at this point, because after we have finished writing to the volatile variable, the next time we are guaranteed to have the values of these variables flushed to main memory is the next time we write to has new frame, which will happen the next time store frame is called. So the result of that is that even though thread 2 will still correctly exit this while loop sooner or later, the value that it is reading from this frame here, this frame field here, could be the value of the frame field as set in the previous call to store frame, right? Because after all, when we flush the values of has new frame here, then we have not yet set the new value of frame, and which means at this point in time we might be flushing the old value here, and that might be what thread 2 is seeing. It could also be, there's no guarantee that this is what will happen. It could also be that somehow the write to this frame here is actually flushed to main memory, and so that thread 2 actually sees the new frame, but there's just no guarantee that this happens, right? Whereas in this ordering here, we have a guarantee that once has new frame changes to true, this dot frame will point to the latest frame set by thread 1. And so, as you can see, instruction reordering may break the visibility guarantee of the store frame method. In order to fix the problems with that potential instruction reordering can cause with regards to visibility of volatile variables, Java has introduced the volatile happens before guarantee. And there's a guarantee both for writing to volatile variables and reading from volatile variables. And I will start over here on the left by explaining the happens before guarantee related to writes to volatile variables. So any write to a field or variable that happens before a write to a volatile variable will remain before a write to a volatile variable. So none of these two instructions here can be reordered to happen after the write to has new frame, because has new frame is declared volatile, as you can see up here in this line. These two instructions can still be reordered among themselves. So this instruction could be reordered to occur before this instruction up here, but they cannot be reordered to happen after this write to the volatile variable. Similarly, any read of a volatile variable that is located before reads of other non-volatile or volatile variables are guaranteed to happen before any of these subsequent reads. In this particular case here, it means that the read of has new frame inside here, the while loop here, cannot be reordered to happen after this read down here. In other words, the read of has new frame is guaranteed to happen before the read down here of this dot frame, and that is because has new frame is declared volatile. Now, in this particular case here, reordering the instructions so that this read of this dot frame happens before the while loop would completely change the semantics of the method here. So this reordering is not actually allowed. But in case this had just been a normal read of has new frame here and not happened inside a while loop, inside the condition of a while loop, then even then reordering the instructions so this dot frame, the read of this dot frame here would happen before the read of has new frame would not be allowed. And that is the Java volatile happens before guarantee that puts that restriction on instruction reordering for volatile variables. Java has a similar challenge around instruction reordering around synchronized blocks in Java, and in order to illustrate these problems, I have created a new example here. It is similar to the previous example. You have two threads which are exchanging values through a value exchanger, and there will be a single instance of the value exchanger stored here in main memory, but each of the threads might keep local copies of the values inside of this value exchanger instance during execution. Thread 1 here will call set values, or set, and with the values object here as parameter, and that will copy the values of the values object inside these three local or private fields. And thread 2 will call get, providing a values object into which the values of these three private fields is copied. The Java synchronized blocks visibility guarantee says that when a thread enters a synchronized block, like for instance over here, the thread will refresh all variables that are visible to the thread at that time, and it will refresh them from main memory. So when thread 1 enters this synchronized block here inside of set, it will first refresh all the values of val A, B, and C from main memory. And after that, it will copy these new values from the values object here into these fields. And when it exits, when thread 1 exits the synchronized block again, all variables visible to the thread will get flushed back into main memory. So at this point in time, val A, B, and C will be flushed to main memory. As you can see over here, we have a similar situation when thread 2 calls get. By the time it enters this synchronized block here, it will refresh the values of val A, val B, and val C from main memory from over here. So it sees the values that were written by thread 1. And at the time the thread 2 here exits this synchronized block, any change the fields would be flushed back to main memory. However, in this particular case, we are not really flushing anything. We're not really changing anything inside of value exchanger. We're only changing something inside of this V object here. So it is not so important that they're flushed back, but they will be flushed back, whatever was changed. Now imagine that the instructions in these two methods were reordered, right? So that this assignment here to val C was reordered to happen outside of this synchronized block here. And the read of val A was reordered to happen outside of the synchronized block over here. Now, this reordering would change the visibility guarantees of the code, right? Because by the time thread 1 exits this synchronized block here, only val A and val B have been changed. And so by the time the values of all these three variables are flushed back to memory, only val A and B reflects the new values from V. When we assign a value to val C later on, there's no guarantee that this will get flushed back to main memory, at least not until the next time thread 1 exits this synchronized block here. Now, it could be flushed back to main memory, but there's no guarantee that it will be. And that means that now val C may not be correctly reflected in main memory. Similarly, when we are reading val A here, val A here, this dot val A may not yet have been refreshed from main memory. So this could be an old value that we're reading from val A, right? Whereas when we enter this synchronized block here, then we are refreshing the values of val A, B, and C from main memory. And thus down here we are assigning the correct values to val B and val C, but val A could actually be assigning a wrong value. And actually val C could even be assigned a wrong value too, because of the reordering that happened over here. So val C may not be correctly flushed to main memory. So even if we are reading the latest value of val C from main memory, what is stored in main memory would still be wrong because of this reordering. So as you can see, instruction reordering around synchronized blocks may break the visibility guarantees provided by these synchronized blocks. In order to fix these problems regarding instruction reordering around synchronized blocks, Java synchronized blocks also come with a happens before guarantee. And the happens before guarantee of a synchronized block is, first of all, that any write to a variable that happens before the exit of a synchronized block is guaranteed to remain before the exit of a synchronized block. So this write here, none of these writes here can be reordered to happen after the exit of this synchronized block here. And this also counts for writes to variables that would happen before this synchronized block, right? If two of these writes were happening outside of the synchronized block, they could still not be reordered to happen after this synchronized block exits. Similarly, for reads, the entrance to a synchronized block that happens before a read of a variable is guaranteed to remain before any of these reads to variables that follow the entrance of the synchronized block. So in other words, none of the reads here of these variables here could be moved or reordered to happen before we enter thread 2 enters the synchronized block over here. And that would also be true of reads that happen after the synchronized block here. They cannot be reordered to happen before this synchronized block here is entered. So to summarize, a write that happens before the exit of a synchronized block cannot be reordered to happen after the exit of a synchronized block. And similarly, a read that happens after the entrance of a synchronized block cannot be reordered to happen before the entrance of this synchronized block. There are additional nuances to the Java happens before guarantee, some of which I have listed in this slide. However, rather than listing every single guarantee throughout all the Java APIs, I will just summarize it with the definition I had in the beginning, that the Java happens before guarantees are all sets of restrictions on instruction reordering to avoid instruction reordering breaking the Java visibility guarantees in various ways. So the Java happens before guarantees exist in order to make sure that communication between threads works correctly. That's it for this video about the Java happens before guarantee. Remember to check out the description below the video for a link to a textual version of this tutorial, as well as other related tutorials. If you like the video, hit the like button, and if you want to see more videos like this, subscribe to my channel, and I'll see you in the next video. A Java synchronized block is a block of Java code which can only be executed by one thread at a time. Synchronized blocks are marked using the synchronized keyword in Java. In the class here on the left, you can see how I have used the synchronized keyword to declare two methods synchronized. And that is the set object method here. You can see I've used the synchronized keyword here, and the get object method here. Declaring an instance method synchronized means that only one thread can execute that method at a time on a given instance of that class. Now, and the getObject method here. Declaring here, see how I have used the synchronized keyword to declare two methods synchronized. And that is the setObject method here. You can see I've used the synchronized keyword here, and the getObject method here. Declaring an instance method synchronized means that only one thread can execute that method at a time on a given instance of that class. Now in the case here where we have two synchronized methods, it also means that only one thread can execute either this method or that method because both of them are synchronized. If you do not want to declare a complete method synchronized, you can also just create a synchronized block inside of a method. And I have two examples here in the setObj method and the getObj method here. As you can see, I have declared two synchronized blocks inside of each of these methods. A synchronized block can also only be executed by one thread at a time. And that means that this synchronized block here and this synchronized block here can only be executed by one thread at a time. Notice the object that is specified inside the parentheses of these two synchronized blocks here. This is called a monitor object, and the monitor object is the object note, and this synchronized block here can only be executed by one thread at a time. Notice the object that is specified inside the parentheses of these two synchronized blocks here. This is called a monitor object, and the monitor object is the object on which these methods or these blocks here are synchronized. And if you look at the methods up here, they are declared synchronized, and that is the same as synchronizing them on the this monitor object. So that means that all of these synchronized blocks here, the two methods up here and the two synchronized blocks here, are synchronized on the same monitor object, which is the this instance. The effect of synchronizing the two methods setObject and getObject and the two synchronized blocks inside of setObj and getObj on the same monitor object is illustrated here on the right. In this example, we have a single synchronized exchanger instance which is shared between two threads. Thread 1 regularly calls setObject or setObj. It doesn't really matter which of these two methods is called because they do the same thing. And because all the code inside of setObj is located within a synchronized block, which is synchronized on this object, the synchronized exchanger instance as monitor object, the effect of calling any of these two methods is the same. Thread 2 calls getObject and getObj on a regular basis. And again, it doesn't really matter which of these two methods is called because the synchronized semantics of these two methods is the same. Because setObject and getObject and the synchronized blocks inside of setObj and getObj are all synchronized on the same monitor object, the instance of the synchronized exchanger class, that means that only one thread can enter any of these synchronized blocks at a time. So if thread 1 is currently executing inside of setObject, then thread 2 cannot enter getObject or the synchronized block inside of getObj at the same time. If instead thread 1 and thread 2 each had their own synchronized exchanger object, which they were calling setObject and getObject on, then the synchronized methods and synchronized blocks inside of each of these instances would be synchronized on the instance itself, meaning that when thread 1 calls setObject in this instance here, that only blocks other threads from calling any other of these methods on this instance, not on this instance. And in the same way, when thread 2 calls any of these get object or get obj methods over here, that only blocks other threads from calling synchronized methods or entering synchronized blocks, which are synchronized on this instance here. So the monitor object of the synchronized blocks matter. To recap, let's have a look at the code over here on the left again. The two methods here are instance methods because they're not declared static. So that means that these two methods here belong to the instance. So any synchronized exchanger instance, they will belong to, and you can call them on that instance. Because the methods are declared synchronized, that means they're synchronized on the synchronized exchanger instance. That is the monitor object these two synchronized methods use to guard access to these methods for threads. And that is similar to what we have done down here, where the synchronized block uses this as a monitor object, and also here. So that has the same effect. Synchronized instance methods are always synchronized on the instance method belongs to. But synchronized blocks can be synchronized on any Java object you want to use as monitor object. And I will show you examples of that later on. Let's just see an example of using the static synchronized exchanger here and having a thread 1 called set object and a thread 2 called get object. And I have an example here on the left. Now, as you can see, first I create a synchronized exchanger instance here. Then I create the first thread, which loops it's given a runnable. And this runnable loops 1000 times, and for each iteration in the loop it calls set object with the string version of I. So it concatenates the empty string with I and sets that on the exchanger. Then we have thread 2 down here, which is also given a runnable, and this runnable also loops 1000 times, and it prints out whatever is returned from get object on the exchanger instance here. And then finally thread 1 and thread 2 are started, and let's run this example and see what is printed out. As you can see, we get a lot of prints outs from the second thread. Start with a lot of nulls, and that is because it calls get object before thread 1 has called set object the first time, and this has to do with thread scheduling. So there's no guarantee about the exact order in which thread 1 and thread 2 gets access to the exchanger. They just cannot get access at the same time. But as you can see, thread 2 gets access a lot of times before thread 1 has even called set object even once. But as you can see here, all of a sudden thread 1 gets access, right? And it starts calling set object, and you can see that it reaches to call it 192 times before thread 2 gets a chance to come back and get the object, right? And then you see 7 times, no, actually more, it's more than 7. This is 13 times before get object is called the second time, and then another 8 times, and as you can see, there's some gaps here, right? So that means that now thread 1 gets to call exchanger multiple times before thread 2 gets a chance to call get object again. And then you can see it ends up here at 999, and that is the last value that thread 1 sets because it runs until I is less than 1000. So that is how it looks when two threads are sharing a synchronized exchanger here and calling set object and get object. You can also use the synchronized keyword with static methods and create synchronized blocks inside of static methods. And here on the left, I have created an example of the synchronized exchanger in a static version. First of all, you can see that the object variable up here is now static, and the method set object and get object and set obj and get obj, they are all declared static. A static synchronized method uses the class object of the class the method belongs to as monitor object. So that means that instead of using the instance of the class, as is the case with instance methods, it uses the class object. And that is because static methods do not belong to any instance, they belong to the class. And you can see down here in the set obj and the get obj methods that I have used the static synchronized exchanger.class as monitor object for these two synchronized blocks, and that has the same effect as declaring the whole method up here synchronized. Just to recap, let me show you here in the diagram on the right how that works. We have one thread here. Imagine you have one thread here calling set object or set obj. It doesn't really matter in this case. And you have another thread calling get object or get obj. And since these are static methods, and this is a static variable, right? Otherwise we couldn't access it from inside of static methods. But since these are static methods, only one thread in total can call any of the methods that are synchronized on the static synchronized exchanger class as monitor object. So when thread 1 calls set obj, thread 2 has to wait. When thread 2 is calling one of these methods, thread 1 has to wait. It is also possible for a class to contain both static and instance methods, non-static methods, which are synchronized. And I have created an example here on the left. You can see that the class mix synchronization here contains a static variable and a static synchronized method which can set a value for the static variable. And then we have here a field, an instance field, and we have a synchronized instance method which can set a value for this field. And I've left out the getter methods just to keep the example simple. Even though these methods belong to the same class, the two methods are not synchronized on the same monitor object. This static synchronized method here is synchronized on the mix synchronization class object, whereas the instance method down here is synchronized on whatever instance of mix synchronization that the method is called on. This difference in monitor object means that you can have one thread calling set static obj at the same time as an instance method here is called on an instance of mix synchronization by another thread. However, if two threads were to attempt calling set static obj at the same time, of course they would be blocked because they would try to enter the same synchronized block, which is synchronized on the same monitor object. Similarly, if two threads were to call set instance object here on the same instance of mix synchronization, then they too would block each other out. Whereas if two threads were calling set instance obj on two different instances, well, then these two methods would be synchronized on two different instances of mix synchronization. They would be using two different monitor objects, and thus the two threads would be able to call these two methods on different instances at the same time. It is actually possible to use different monitor objects for different synchronized blocks, even within the same class, and I've created an example here. In this class, I have created two monitor objects. These are just object instances. It could be any type of object, but right now I've just used object for simplicity. Then I have created two counters here, two counter fields, and then an inCounter1 method, which has a synchronized block, which is synchronized on monitor 1 on this object instance up here. And inside of that, we increment the counter1 variable. Inside inCounter2, we have a synchronized block, which is synchronized on the second of these monitor objects, monitor 2. And inside of this synchronized block, we increment counter2. Because these two blocks use different monitor objects, these two synchronized blocks, they will not mutually exclude threads from entering them. So that means that we can have one thread calling inCounter1 at the same time as another thread can call inCounter2 on the same instance of multiple monitor objects. And of course, if you had different instances, then of course they would also internally be using different monitor objects, and so they wouldn't block at all. However, on the same instance, only one thread can enter this synchronized block here, and only one thread can enter this synchronized block here at a time. It is even possible to share monitor objects between different instances of the same class, or even between instances of different classes. And I've shown you a simple example here in this class here, shared monitor object class. As you can see, it has a object monitor variable here, and that variable gets set in the constructor here, right? So when you create a shared monitor object instance, you pass whatever object you want to use as a monitor, and we set that monitor into this monitor field. And you can see down here that in the inCounter method, that the synchronized block here is synchronized on the monitor object passed in here into the constructor and set into the field. Now, one thing to be aware of is that a monitor object cannot be null. It must not be null. If it is null, then you will get a null pointer exception when you try to enter this synchronized block here that is synchronized on that monitor object. So that is why I've inserted this if statement here that checks if the monitor is null, then we throw an exception. Let me quickly show you an example of how to use these shared monitor object and how to pass a monitor object to the instances of shared monitor object. Here's a simple example here. I create an object calling it the variable monitor1, and you can see I create two shared monitor objects instances which will have monitor1 passed as monitor object to their constructors. That means that the synchronized blocks inside of inCounter, inside of these two instances, will actually synchronize on the same monitor object, and thus calls from different threads to either SMO1 inCounter or SMO2 inCounter will actually block for each other, right? Because they use now the same monitor object. The synchronized blocks inside here will act as if this was kind of the same instance, but it's not. It's because the monitor object is the same for the synchronized blocks. However, down here in this last example here, we create a separate new monitor object, and this shared monitor object here uses this monitor object to synchronize on. And that means that for SMO3, the inCounter calls, if a thread calls an inCounter call here, it will not block other threads from calling inCounter on SMO1 and 2, because these two instances here use the same monitor object for the synchronized block inside, and this instance here uses a different monitor object for the synchronized block inside, as you can see here, right? The monitor object is taken as parameter to the constructor, and then the encounter synchronizes on that object. Here's a different way to illustrate what is going on in the previous example. Imagine the blue boxes here are objects, and the red boxes here are synchronized blocks within these objects. And these red circles here are monitor objects. Then we have two objects with synchronized blocks inside, which are synchronized on a shared monitor object. And we have a third object here with its own synchronized block, which is synchronized on its own monitor object. Now, if a thread calls this object here, enters this synchronized block, then it will be, because it's sharing the monitor object with this synchronized block, it will block threads both from entering this synchronized block and also this synchronized block. However, a thread could easily call this object here, this synchronized block could easily enter here because it is synchronized on a different monitor object, right? So of course you cannot have two threads entering this synchronized block, but you can have one thread entering this synchronized block and another thread entering either of these ones, not both of them, one of them. Sharing monitor objects between different instances is an advanced technique, and you can create some very interesting and very advanced synchronization mechanisms across various classes and instances of the same class or instances of different classes. However, a word of caution: once you start sharing monitor objects between different instances and even between different classes, it becomes a lot harder to reason about whether your final solution actually synchronizes correctly as intended. Just one final comment about monitor objects, and that is there are some classes you should never use as monitor objects. For instance, you should not use strings. For instance, if you did like this, like this, the problem is that you don't know how the Java compiler will optimize this behind the scenes. You don't know if these two strings here will actually be different string instances, or if the Java compiler behind the scenes will optimize this to be the exact same string instance. So in general, using string constants as monitor objects is a really bad idea. It's to stay on the safe side, use any object which is not a string, which is not one of the primitive wrapper types like integer or long or whatever. Just stick to using objects or instances of your own classes. It is actually also possible to have a synchronized block within a lambda expression, a Java lambda expression. And if you're new to Java lambda expressions, check out the description below this video and you will find a link to my Java lambda expression tutorials. In this example here, in this synchronized lambda class, we have a single private static field object. We have a static set object method, which is also synchronized here, as you can see. And then we have a static consume object method. Which takes a consumer as parameter. This method is not synchronized, so for this to synchronize properly with the set object up here method, the lambda expression would have to provide synchronization. Now let's have a look at how calling this method, consume object method, looks in practice, right? So we call consume object, it's a static method, and we pass a lambda expression here as parameter to consume object. Now as you can see, this lambda expression inside the body has a synchronized block, and it's synchronized on the class object of this class. Now that is done to make sure that the lambda expression here, the synchronized block here, will synchronize on the same object, the same monitor object that this synchronized method up here is synchronized on, because this is a static synchronized method. It will also synchronize on the class object for the synchronized lambda class. And yeah, consume object will call accept, and when that happens, this method here gets called, this lambda expression gets called, and whatever thread calls it will enter this synchronized block and print out the value of the object. Now down here you can see that it is possible to use a different synchronizer, a different monitor object than synchronized lambda.class. However, if you do so, set object and consume object no longer synchronizes on the same monitor object, and you will not have an effective blocking of between the blocks. So a thread calling set object will not block for threads calling consume object, because the synchronized block here uses a different monitor object. Now, since lambda expressions do not belong to any object instance, you cannot use this as a monitor object because there is no this object in the context of a Java lambda expression. But any other instance you can get a hold of that you can access from within the lambda expression can be used as a monitor object. Just make sure that whatever object you choose makes sense. So in this case, using string.class did not make sense, right? It was just an example. whereas synchronized lambda.class does make sense because it makes consume object with this lambda expression synchronized on the same object as the set object method. Java synchronized blocks are reentrant, and to explain what that means, have a look at this example here. This class has two methods, both of which are synchronized. And that means that the synchronized blocks that these methods are making up are synchronized on the instance of the reentrance on which these methods are called. So look at this. In case a thread calls this inc and get method, then inc and get calls to inc, which is also synchronized. However, since the two methods are synchronized on the same monitor object, and it is the same thread that calls both of these methods, then this second synchronized block will not block the thread calling it from inside the first synchronized block. And that is what reentrant means. It means that a thread that already holds the lock on the monitor object a given synchronized block is synchronized on, is allowed to enter a new synchronized block which is synchronized on the same monitor object. And that is what is going on here, right? First, we take the thread that calls inc and get, takes the lock on the monitor object that this method is synchronized on, which is the instance that it is called on, the method is called on. And then when inc is called, the Java virtual machine here detects that, oh, it's the same monitor object that this block is synchronized on, and it's this thread that calls it already holds that lock on that monitor object, so it is allowed into this method. So it is said to be reentrant. Java synchronized blocks affect the visibility of changes to variables that are visible to multiple threads. The way synchronized blocks affect the visibility of changes to variables that are visible across different threads is also sometimes referred to as the Java synchronized visibility guarantee. To illustrate the Java synchronized visibility guarantees, I have created this diagram here as well as this very simple example class here. As you can see, the example class contains a single counter variable here, count, and an inc method with a synchronized block inside which increments the count variable, and a get method which also contains a synchronized block which returns the value of the count variable. Imagine too that we have a single instance of the sync counter stored in main memory, and that we have two threads, each running on separate CPUs, accessing this shared sync counter instance. When thread 1 calls the inc method on the shared sync counter instance stored in main memory in here, what happens is that the count variable is read from main memory through the cache into the CPU registers here. In here, the count variable is incremented, and then it is written back to main memory. More specifically, what happens is that when thread 1 enters this synchronized block, all variables that are visible to thread 1 will be synchronized from main memory, means they will be read in from main memory. And that means that if the thread had any cached values here of that variable, then they will be overwritten with the fresh value from main memory. So in this case, the count variable here, the field, is visible, so that will be read from main memory through the cache into the local CPU registers. When the thread exits the synchronized block again, all variables that are visible to the thread at this point will be synchronized back to main memory, means they will be written back to main memory. So any old value stored here in memory will be overwritten with the latest value of the variable that is visible to the thread. So in this case, the count variable is visible to the thread, and so the count variable will get written back through the cache to the main memory again. The same happens when thread 2 calls the inc method. It enters the synchronized block, reads a fresh value of the count variable into its local cache and into its CPU registers, increments the count variable, and writes the value back to main memory. If we remove the synchronized block around the operation that increments the count variable, what would happen is that there would be no guarantee about when thread 1 refreshes the value of the count variable from main memory, nor would there be any guarantee about when it writes the count variable back to main memory. And the same would be true over here, and thus you could have a thread 1 read the value 0 in here, increment the count variable, but keep it locally cached here and never commit it back to main memory. And when thread 2 tries to call inc as well, it will also read the value 0 into its CPU, and then it would increment the value, and then maybe it would write it back, maybe it would just keep it cached here. Sometimes the write would go back to main memory, but sometimes not. And that means that a lot of the increments done by thread 1 would not be visible to thread 2, and a lot of the increments made by thread 2 would not be visible to thread 1. So if each of these threads were to execute inc 10 times each, the result could be anything from 10, the final result could be anything from 10 to 20, because they would overwrite each other's updates, right? You could have this thread here, increment count to 10, and then at that point write the value back to main memory, and you could have thread 2 do the same thing without ever seeing any of the updates from thread 1, and so the final result would be 10 when it should have been 20. With the synchronized blocks in place, you are guaranteed that, first of all, that the variables are always read in from main memory when the thread enters the synchronized block, and that whatever changes have been made are written back to main memory when the thread exits the synchronized block. And since the synchronized block also makes sure that only one thread at a time can enter the synchronized block, that means that you cannot have two variables reading count at the same time, increment it, and then write the value back on top of each other. Only one of the threads gets to increment the variable at a time, and thus none of the increments will get lost. Let me quickly show you the difference between having a counter which is not synchronized and one that is, and how that affects visibility. Look at this counter here. Yes, it's called sync counter, but the count method here, the int count method and the get count method, they are not actually synchronized at all. Now, in this example, you can see I create a single sync counter, and then I create one thread here, which will loop 1,000,000 times and call inc count, and then print out whatever the final count is, and another thread that does exactly the same thing. And because they use the same counter instance, they both reference the counter instance here, well, then the total result should be 2,000,000, right? Whatever thread finishes first will not see, of course, a total of 2,000,000, but the last thread that finishes should see the result 2,000,000, right? Because each of them have counted 1,000,000 and incremented the count in the counter for every iteration in the for loop. And when we run this code, you can see that the second thread here only gets to 1.8 million, 1.9 million or so, not even the same number every time. Now let's see what happens when we make these methods synchronized. Synchronized void here and synchronized down here. Now, first of all, only one method or one thread can call the int count method at a time, which means that they cannot copy the same value. Two threads cannot copy the same value, then increment and then override each other's updates. First of all, and second of all, whatever value gets written here, get updated to, that will be written back to main memory, right? So the next thread, the second thread, will see it. Now let's try to run this example again and see the difference. Now you can see the second thread reaches a total count of 2,000,000. Let's try to run it again and see that it reaches that consistently. Now you see both threads reach 2,000,000. And now you can see the second thread reaches it. Again, 2,000,000. So here is a fine example of how you can fix these data visibility problems using synchronized blocks. Java synchronized blocks also come with a happens before guarantee. And I have covered the happens before guarantee in a separate video. And if you check out the description below this video, you can find a link to it. So I won't get into too much detail about the happens before guarantee here, but I will still quickly just sum up what it is about. Now, the CPU and the Java virtual machine and the Java compiler as well, they are allowed to reorder the instructions of your code if they think that reordering the instructions will make the code execute faster. However, the compiler and the CPU can only make this a determination from its own perspective, meaning from a single-threaded perspective. So have a look at these cases here. We have a synchronized exchanger here called syncEx, and it has a set method here with a synchronized block inside. And inside of that, we increment the count, which is the number of objects that have been exchanged, or set. And here we just simply set the object to point to the object passed here as parameter. Now, we're guaranteed that when the thread that calls set enters this block, that the count variable is read in from main memory. And actually, this .obj is also written from main memory, but since it is overwritten just after, it doesn't really matter. However, when the thread calling set exits this synchronized blocks, we are guaranteed that the values of both count and object obj will be written back to main memory. Now, imagine that the Java virtual machine or the compiler or the CPU reorders the instructions, so the execution becomes as scheduled or sketched here on these two examples here on the right. In the first reordering example, the instruction this.count++ has been moved up above the synchronized block, so outside the synchronized block. And that means that this instruction is no longer covered by the synchronized block's visibility guarantees. More specifically, this means that we no longer have a guarantee that the thread calling set will refresh the value of count from main memory before incrementing it. And thus we don't know if we are losing some increments made by other threads. However, we do have a guarantee that once the thread exits the synchronized block here, that it will write whatever value that this.count has back to main memory, because even though it's accessed outside of the synchronized block, it is still visible to the thread that exits the synchronized block here. here, so it will still get synchronized back to main memory. However, as long as the thread doesn't properly refresh it from main memory, we can no longer trust the value of the count variable. In the second reordering example, the this.count instruction has been moved outside and below the synchronized block. And semantically, it looks like this code is still doing the same thing because these two instructions are independent of each other. They do not depend on the result of each other. However, now with the this.count instruction, count plus plus instruction down here, this instruction is now no longer guaranteed to be written back to main memory. We don't know when it will be written back. We do know, however, that whatever thread calls set will refresh all of the visible variables from main memory by the time it enters the synchronized block here. So both the value of count and obj will be refreshed from main memory. However, we do not know if the incremented value here will get written back to main memory or not. As you can see, instruction reordering may break the visibility guarantee of Java synchronized blocks, and that is why synchronized blocks come with a happens before guarantee, which puts some restrictions on what kind of instruction reorderings are allowed around synchronized blocks in Java. For the finer details, I have to refer you to my Java happens before video, and you can find a link to that in the description below this video. The Java synchronized block construct has a few limitations. First of all, only one thread can enter a synchronized block at a time. And there are some situations in which this limitation can be annoying. For instance, maybe you only wanted one thread to be able to write to a certain object at a time, but you would like to have multiple threads be able to read the values at the same time, as long as there's not another thread writing at the same time. And you cannot do this with just a synchronized block. However, you can use some of the read-write logs that are part of the JavaUtil concurrent package to achieve that effect. The second limitation here is that there's no guarantee about the sequence in which waiting threads gets access to the synchronized block. And that means that if you have two threads that are waiting, and then one gets access and the other one has to keep waiting, and then another thread comes and gets enqueued waiting to get into the thread, so you have two waiting threads again, then there's no guarantee that the first thread that has waited the longest time is then actually allowed in the next time. This is normally referred to as fairness. And because the Java synchronized block construct does not guarantee fairness, you risk what is called starvation. However, there are implementations of locks in the JavaUtil concurrent package which provide such fairness guarantees, and you can use them instead if you want to achieve absolute fairness of the waiting threads. Entering and exiting synchronized blocks incurs a small performance overhead on your application. How big this performance overhead is depends on the situation. In situations where a thread tries to enter a synchronized block and that synchronized block is not already occupied or locked by another thread, then this performance overhead is quite low and you shouldn't worry about it. However, in situations where, for instance, a thread 2 is trying to access a synchronized block where another thread is already executing inside, then thread 2 gets blocked. And this incurs a higher overhead for thread 2 than it did for the first thread entering the synchronized block. And on top of the performance overhead associated with being locked and having to wait and being notified later on, the thread, of course, also loses all the time that it has to wait until the first thread here has finished executing inside of this synchronized block. One final thing to notice about synchronized blocks in Java is that they can only block threads that are running within the same virtual machine. So if you have an application that is running on a cluster of machines, a cluster of virtual machines, then a thread entering a synchronized block in virtual machine 1 will of course never be able to block a thread that is entering a synchronized block in virtual machine 2. If you need such cross virtual machine locking, you will need to use another mechanism, either design one yourself or use, for instance, a database which also has locking capabilities, or find some open source tool that provides that functionality. That's all for this video about the Java synchronized keyword and synchronized blocks in Java. Remember to check out the description below the video for a link to a textual version of this tutorial, as well as link to other related tutorials. If you like this video, please hit the like button, and if you want to see more videos like this, please subscribe to my YouTube channel. The Java volatile keyword is a special keyword which can be applied when declaring a variable. As you can see in the example here on the left, I have declared the second variable volatile by adding the volatile keyword here to the variable declaration. By declaring a variable volatile, you tell the Java virtual machine that this variable must always be read directly from main memory, and when the variable is changed, the changed value must be written directly back to memory immediately. If a variable is not declared volatile, we have no guarantee about how often the variable will be read from main memory here up into a CPU register, and how often, when the value is changed up here, the variable is changed up here in the CPU register, that this value is written back to main memory. This will happen from time to time, but there's no guarantee about when it happens. So if you imagine for a second here that neither of these two variables were declared volatile, so both of them are not declared volatile, then what could happen is you have thread 1 calling set object here. It sets 2 new values for object and has new object, but the Java virtual machine decides to keep these values only in the CPU registers here and not pushing them back to main memory. So when thread 2 here calls get object down here and it tries to look at has new object, well, then it sees maybe it sees the old value which is stored in main memory, or maybe it sees an old cached value of has new object which it has stored in its own registers from last time it called get object. So, and the same is then true down here with the object variable. It might see an old version read from main memory, or it may have an old cached version over here. So as you can see, if we do not declare any of these two variables volatile, then we will have some visibility problems. And the Java volatile keyword helps with these visibility problems by providing a visibility guarantee, which I will explain shortly. The Java volatile keyword visibility guarantee is as follows. Whenever you write to a volatile variable, then that variable and all other variables that are visible to that thread will be written directly back to main memory. As you can see here, the has new object is declared volatile, but the object variable is not declared volatile. So in the case here, when thread 1 calls set object, then at the time we set a new value for object, well, object is not volatile, so we are not forced to write anything back to main memory yet. But when we set has new object to true, then because you can see here that has new object is volatile, we are forced to write that value back to main memory and all other values that are visible to the thread at that time. Now, when I say we are forced to write it back, it is the Java virtual machine that is forced to write it back, and it happens behind our back. So this is not something that we are actively engaged in. It just happens. Similarly, whenever a thread reads a volatile variable, then the value of that volatile variable has to be read directly from main memory. Additionally, any variables that are visible to the thread at the time it reads the volatile variable also has to be refreshed from main memory. So in the example up here, when thread 2 calls get object and it iterates through this loop, and for every iteration it reads this volatile variable here, has new object, which is declared volatile, then the value of has new object has to be reread from main memory. Additionally, because object up here is also visible to thread 2, then the value of object also has to be reread from main memory for every iteration in this while loop. So as soon as thread 1 changes the value of has new object here, then the value of has new object and object will be pushed to main memory and will thus become visible to thread 2. And then thread 2 will exit this loop and will read the correct value of the distant object variable, because this object will also be refreshed from main memory. And then thread 2 will set has new object to false, which will again cause has new object to be flushed back to main memory here. And of course the rule is the same, that all other variables that are visible to thread 2 will also be flushed back to main memory at this time. The Java compiler and the Java virtual machine are allowed to reorder instructions in your application as long as the reordering does not change the semantic meaning of the application. Unfortunately, instruction reordering may break the Java volatile visibility guarantee, causing your application to malfunction in a multi-threaded situation. Let me explain via this diagram here created for that purpose. We have created here a new class called exchanger2. It has 3 variables here, of which only one of them is declared volatile. Now imagine you have thread 1 calling set values here, and so from this values object here it will obtain value 1 and value 2, set it to assign the values to val 1 and val 2 up here, which are not volatile, so nothing will get written back to main memory just yet. Then val 3 from the source object here will be assigned to val 3, and because val 3 here is volatile, then we have all the variables here, all the values here being pushed to main memory at this point in time. Similarly, you can see here in get values, when thread 2 calls get values, we start by reading val 3, and from this to val 3, right? And because val 3 is volatile, that means that at this point in time here, both val 3, 2, and 1, all of them are read in from main memory. And so that means that in whatever CPU registers are stored here, then that means that we have now the freshest values here stored in the CPU registers, right? So val 3 is written then into the destination values object here, and these 2 other just recently refreshed values will be written into val 1 and val 2 of the destination values object as well. Now, this worked just fine as long as the sequence of these instructions are not changed, right? For this to work, over here, setting or reading val 3 must be the last thing that happens here, or setting val 3 here must be the last thing that happens here, so that we push all these 3 freshly changed values to the main memory. And over here, the reading of val3 must be the first thing that happens over here, so that we refresh all of these values, val3, 1 and 2, directly from main memory at this point in time before setting them into the values object. Now imagine what happens if the Java virtual machine or the compiler decided to say, hey, it doesn't really matter in which sequence these instructions here are executed, right? In the end, all that happened is that val3, val1, and val2 are set into this destination object. So why could I not change the sequence here? Or over here, it doesn't really matter in which sequence we read the values out of the values source object here and write them into val1, val2, and val3, and decided to reorder the instructions. Then, obviously, the time at which the values are forced written back to main memory and forced read from main memory will change. To illustrate the problems that instruction reordering may cause, look at this modified version of the exchanger2 class, and imagine that instead of having val1 here assigned as the first instruction up here, it has been reordered so that it is now executed as the last instruction over here in set values. Now, notice what happens is that first we set the value of val2, which does not cause any synchronization to main memory. Then we read the value of val3 here from the source object and set val3. And because val3 is volatile, then at this point, both val1, val2, and val3 are forced synchronized back to main memory because all three variables are visible to thread 1. However, we have not yet set the new value for val1, so the value for val1 that is flushed back to main memory is an old value. Now you can see here that the instruction reordering of moving the assignment of val1 down here after val3 causes a Java volatile visibility problem. We are breaking the visibility guarantee of writes. Similarly, imagine that instead of val3 here being read as the first value read inside of getValues here, it is now reordered to be the second variable that is read. Now, because of that, that means that whatever value is stored in the val1 variable at this point in time here is what will be written into val1 of the destination object. And we don't know what that value is. It's probably the one that is stored from the last time set values was called, or getValues was called actually. And then when we read val3 here, because that is a volatile variable, then all of val1, val2, and val3 are refreshed in from main memory at this point in time. So a new value will be read for val1, val2, val3, but val1 has already been set here into val1 of the destination object. And so the new value that is just read in here is ignored. In fact, it will probably be set the next time that getValues is called, but then it's not matching the other two values which were set in the previous call to set values. So as you can see, instruction reordering on the reading side here has also broken the visibility guarantee of the Java volatile keyword. So instead of reading val3 first, we now read val1 first, causing the visibility over here to be to malfunction in a multi-threaded setting. To avoid instruction reordering breaking the visibility guarantee of the Java volatile keyword, the Java volatile keyword also comes with a happens before guarantee. And the happens before guarantee is thus: all writes to volatile or non-volatile variables that happen before a write to a volatile variable will remain before the write to that volatile variable. So over here in this example here in the set values method, the write to val3 here, which is volatile, means that the two writes here will have to remain before this write to val3. So they cannot be reordered to happen after the write to val3. Now these two instructions here can be reordered among themselves. So you can set val2 before val1. That doesn't matter. This reordering is allowed, but neither of them can be reordered to happen after the write to val3. So all writes that happen before a write to a volatile variable will have to remain before the write to the volatile variable. Similarly, all reads of a volatile variable that happens before reads of other non-volatile or volatile variables will have to remain before subsequent reads of volatile or non-volatile variables. So in this situation here in getValues, that means that this read of a volatile value here of a volatile variable val3 will have to remain before the reads of val1 and val2. And so that means that the reading of val1 and val2 can be reordered among themselves, but neither of these two instructions can be reordered to happen before the read of val3, right? So the reading of the volatile variable will remain before any subsequent reads of volatile or non-volatile variables. Obviously, this direct reading of volatile variables from memory and writing of variables directly back to memory after updating them causes a small performance penalty. So you should only use volatile variables when you actually need the visibility guarantees provided by volatile variables if you do not need that. If you are writing some code in a single threaded context, you should not use the volatile keyword. So you should think about it. It's not going to completely ruin the performance of your application, but it will slow it down. So if your application is performance sensitive, there's no reason to use the volatile keyword, except in the cases where you actually need visibility of data between threads. You should keep in mind that using a volatile variable is not always enough, and I will illustrate why using this example here. Look at this counter. Imagine that we have a single counter instance and we have two different threads, or maybe more, calling the inc method concurrently. Now, you can see that the count variable up here is declared volatile, so we will always read the value of the count variable directly from memory, and we will also always write the value directly back to main memory when updated. Now, imagine if the count is 9 and we have two threads entering here inc at the exact same time. Both of them will execute this if statement. They will see that count is not equal to 10. Both of them will see that because count was 9, right? And so both of the threads will progress beyond the if statement here, and both of the threads will execute the count plus plus instruction here, the incrementation of count. Now, first of all, if this was supposed to be a concurrent counter, the fact that the counter is designed to stop at the value of 10 and it still allowed two threads or even potentially more threads to progress beyond this point is clearly a mistake. This is a case where it is not enough that the count variable is volatile. This whole block here should have been declared synchronized as well. So that is one problem, right? So the second problem is that the incrementation instruction in Java is actually not atomic. So the increment instruction consists of a read of the variable, right? So first the variable is read in from main memory. We have an increment of the variable, which happens in a local register in the CPU, and then we have a write of variable directly back to memory. Now, in the case where two threads have progressed beyond this point, well, then both of them will read the value 9 for the value of count, and it's read into a register. Then in that register, both of the threads will increment the count variable, but they will increment their own copy. And both of the threads just read 9, so both of them will increment the count variable to 10. And then both of the threads will write their value back to main memory. Now, clearly, if this had to function correctly, then the total count value should have been 11, right? You have two threads adding 1 to a counter that is 9. That should result in first the variable becoming 10 and then 11 and then written back to main memory. However, both of the threads will write the value 10 back because they read the value of count at the exact same time. Now, obviously, if the threads were just a little bit delayed so that one thread would read the variable, increment the variable, and then write the variable back, then the the second thread would then obviously read the variable value written by the previous thread and then update and increment and write back correctly. However, this is not a guarantee that we have here. This is also possible in the instance that the count variable is 0, right? Both two threads pass beyond the if statement because the count is 0. Then both of them read the value 0, add 1 to it, and write the value back. So both of them write the value 1 back to main memory. And so, as you can see, that is probably not what was intended with this counter here. So instead, you should use a synchronized block or make the whole method synchronized. Or you could use an atomic integer as count variable instead, or one of the many atomic, like an atomic long, or some of the other atomic utility classes in the JavaUtil.concurrent package. So just keep that in mind. Using a volatile variable is not enough always to guarantee correct concurrent behavior. Sometimes you need more. That is all for this video about the Java volatile keyword and the Java volatile visibility guarantee and Java volatile happens before guarantee. Remember to check out the description below the video for a link to a textual version of this tutorial, as well as links to other related tutorials. If you like this video, hit the like button, and if you want to see more videos like this, subscribe to my channel. In some of my earlier videos about Java concurrency and the Java thread visibility, visibility guarantee, you might have heard me say something similar to this. Writes to volatile variables or exiting a synchronized block flushes thread visible variables from CPU cache to main memory. The arrow here on the left represents that claim that the CPU caches are flushed to main memory. However, this is not what happens in reality. What happens is that writes to volatile variables or exiting a synchronized block flushes thread visible variables from the CPU registers to the memory, to main memory. And that is what is illustrated over here with this arrow here. As you can see, thread 4 here is making a write to a volatile variable or exiting a synchronized block, and whatever thread visible variables are stored here in the CPU registers are flushed to main memory. When writing data to memory, the hardware will first store it in the CPU cache, and from there it will eventually get synchronized to main memory. So as you can see here, even though the CPU thinks it is writing the data to the main memory, the underlying caches here will first have the data stored inside of them before it eventually makes its way down to main memory. In practice, the hardware may even choose not to flush the data all the way down to main memory because of a mechanism called cache coherence. The other threads here running on the other CPUs or the other CPU cores, they're actually able to see data stored in the caches over here. Basically what it means is that in case CPU 1 over here, or the core 1 over here, is accessing a variable stored in one address down here, and this core 3 here is also accessing that address, well, the cache coherence mechanism here means that if, say, core 3 here writes to that address, because the CPU register is flushed to that address, then already when it's stored down here in the caches here, then that changed value becomes visible to the other CPUs over here, even if this changed value has not yet been flushed down to the main memory. In practice, the hardware may even choose not to flush the data all the way down to main memory because of a mechanism called cache coherence. The other threads here running on the other CPUs or the other CPU cores, they're actually able to see data stored in the caches over here. Basically what it means is that in case CPU 1 over here, or the core 1 over here, is accessing a variable stored in one address down here, and this core 3 here is also accessing that address, well, the cache coherence mechanism here means that if, say, core 3 here writes to that address, because the CPU register is flushed to that address, then already when it's stored down here in the caches here, then that changed value becomes visible to the other CPUs over here, even if this changed value has not yet been flushed down to the main memory. Sooner or later, though, the hardware will most likely flush the data from the caches down to main memory. And that will typically happen when the hardware needs to store something else in the caches up here, and then there is no longer space for the previously stored values in the cache. But exactly when that happens, you don't know, and your application doesn't know. This is something that is decided by the hardware itself, so it is not visible to the application. That's all for this video about the CPU cache coherence mechanism in relation to Java concurrency constructs such as volatile and synchronized. Remember to check out the description below the video for a link to a textual version of this tutorial. And if you like this video, please hit the like button. And if you want to watch more videos like this, subscribe to my channel. The Java thread local class is a class that is designed to be able to keep a single value internally, but not just a single value, one single value per thread that accesses the thread local. If you look at the diagram here on the right, you can see that we have a thread local in the middle, and then we have two threads accessing it, and thread 1 sets the value 3 into the thread local, and thread 2 sets the value 4 into the thread local, and later when thread 2 wants to access the value of the thread local, it gets the value that it itself had set into the thread local. Whereas when thread 1 later wants to access the value stored inside the thread local, it will get the value back that it itself had stored in there. So the value stored by the two threads do not overwrite each other. They are separate from each other. So even if the thread local instance is the same object, the values kept internally will depend on what thread set them and gets them. If you look at the example here on the left, you can see that the example creates a single thread local of type string, generic type string. That means that you can only insert strings into it, and when you obtain the value from the thread local, you do not need to cast it to a string. You can see that here. Then we have created, the example creates a thread, which first sets the value thread 1, and then sleeps for 2 seconds, and then gets the value out and prints it again. And then the example creates another thread, which sets the value 2 on the same thread local. But remember, the values will be kept separately internally because this is thread 1 and this is thread 2, setting 2 different values. Even if they set the same values, they will be kept separately internally. Then this thread also sleeps for 2 seconds, then gets the value and prints the value out. Now let's try to run this example and see what it prints. And as we expected, we get thread 2 and thread 1 out. Now, the reason the sequence here is reversed from when we start the threads is simply that we have no guarantees of exactly in which order the threads run once they are started. The internal thread scheduler is allowed to schedule thread 2 before thread 1. If we run again here, we might get a different order. See, now we got it in another order here. Just to recap, you set a value into the thread local using the set method, and you get the value out again using the get method. And remember, the value stored internally will be kept separate for each thread. So multiple threads setting a value on the same thread local will not overwrite each other's values. The Java thread local class also has a remove method, which can remove the value stored internally in the thread local for a given thread. And I have created an example here as well. Let me just make it a little bit more readable. As you can see, this thread here sets a value in the thread, gets it again, prints it, so we can see that it has actually been stored, then remove it, and then we get the value again and print it, so we can see it has actually been removed. We should get a null back here. And then we have another thread which is doing the exact same thing here. Except that it waits for 3 seconds in between setting getting the value the first time and then getting the value the second time. And we do that to see that the second thread that is waiting still has its value stored, even if the first thread up here has removed its own value. So when one thread removes its value stored in a thread local, it does not remove the values stored by other threads in the same thread local. Let's run this example here and see what happens. Now, this is the output from the first thread, right? We first insert value, or the value of thread 1, get it, print it, remove it, get it, and print it, right? So thread 1 and null. Then in thread 2, we set the value of thread 2, we get it, we print it. So that's thread 2 here. Sleep 3 seconds, get it, print it. So it's still thread 2 because we have not removed the value thread 2, even if we have already removed the value from the first thread here. Then remove the value, get it, and print it. And as you can see, we end up with a null printed from thread 2. It is also possible to create a Java thread local which contains an initial value, so that if you get the value of a thread local, you will get this initial value if you have not yet set any value, or if the given thread has not yet set a value for the thread local. And the first way to do so here is to create a class that extends the thread local class and overrides the initial value method. And here I'm creating an anonymous class. So as you can see, I override the initial value here and return a new myObject instance. And here's another example where we're creating a thread local using the static factory method. class, which it uses the static method with initial here, right? With initial takes a Java Lambda expression, or actually takes a supplier implementation, and I have then used the Lambda expression to implement the supplier interface. And in this case, the implementation, the Lambda expression here returns a new my object. So like functionally it is the same, but the implementations are slightly different, but the result will be the same of these two thread locals here, 1 and 2. Now, down here I create 2 threads to show how this works. Thread 1 will first call thread local get and print out that value, and then it will call thread local 2 get and print out that value, and thread 2 will do the same thing. Now, what you will see here is that thread local 1 will return an initial value for thread 1, and we can see based on the addresses that are printed out when we print out this my object instance that is returned here, that this is not the same instance, of course, as is stored in get2 or the initial value of get2, but you will see that it is also not the same value as thread 2 gets for thread local 1 and 2. And let me just run this example so it gets a little bit clearer, right? So you can see out here that these are 3 or 4 different my object instances, and that is because first thread 1 creates 2 initial values for itself internally in the thread local, and then thread 2 also creates 2 initial values inside thread local 1 and 2 for itself. So now we have 2 initial values for each thread. So that's 4 my object instances in total. And that basically means that different threads do not share this initial value. I mean, in these cases here, we create identical objects, but the objects are not the same. They are equal, but they're not the same. Instead of using an initial value, it is also possible to simply set the value for the thread local lazily, meaning you first set it at runtime. You do not have a pre-configured initial value set on the thread local. And I have shown you an example here. So in this example, we simply get the value out. If the value is null, then we set another value, and then we get that value here into the value variable and print it. Now, obviously, this will simply print this value that we're setting in here. Now, this way of setting an initial value or a value in general for thread local is not as elegant as using the initial value mechanisms. However, in this way, you are able to insert values that are part of the thread that calls this set method's context. So let's say that you have some special kind of like a date format or something else that comes from the context out here, which cannot be determined at the time the application starts up, at the time you create the thread local, but it can be determined when the thread is finally ready to call the thread local. Yeah, then you can use this method instead. It may sound a little bit complicated, but trust me, the day you need this kind of functionality, you will remember and say, that's what I can use the lazy initialization for instead of an initializer or an initial value. If you are using a thread local from within a thread pool, from when executing tasks inside of a thread pool, then you need to pay a little bit attention. Look at this example here. We have 4 tasks, but only 2 threads, right? So the first and the 4th task are executed by thread 1, and the second and the 3rd task are executed by thread 2. And that, of course, means that the values that are stored inside of this thread local here, when these tasks are executed, will not be completely unique for each task, but only unique for each thread. And so you have to keep that in mind, that in case when executing a task that you are storing a thread local value in here, make sure that you are not reusing a value stored by another thread earlier. And in case you design your code so that it still does, just make sure that that is valid. Okay, so it is perfectly possible to share values between tasks because they're executed by the same thread, but you need to think about it when you design your code. Finally, I just want to show you a special class which is called inheritable thread local. And an inheritable thread local is a thread local which can share its values with child threads created by a parent thread. And to illustrate that, I have created an example here on the left, which first creates a normal thread local, and then it creates an inheritable thread local. And then it creates a new thread here, thread 1. And thread 1 then sets a value inside the thread local and inside the inheritable thread local, and then prints these values out. Now thread 1 creates a child thread, and this child thread also gets the value out of the thread local and inheritable thread local. And what you will see here is that the normal thread local will return null because this thread here is not the same thread that set the value up here. But in the case of the inheritable thread local, you will see that it actually gets the value out because the value is inherited by this child thread because it was set by its parent thread. And the way you find out what is a child thread and a parent thread is simply that the thread here that creates another thread then is the parent of the thread it creates. So this is the child thread, and because this other thread here created it, that's the parent thread. And then this child thread is then started, and thread 1 is started, and we can then see the result. And then we create here another thread here. This is just a normal thread 2. As you can see, thread 2 does not inherit any of the values set by thread 1 and thus you will get 2 nulls out here. Let's run this example here and see that my claims are true. First, we have thread 1, which can get both of the values out that it has inserted into the thread local and the inheritable thread local. Then we have the child thread, which cannot see the value inserted into the thread local, but can see the value inserted into the inheritable thread local. And then you have thread 2 here, which cannot see any of the values because they were set by other threads. That's all for this video about the Java thread local class. Remember to check out the description below the video for a link to a textual version of because local. And then just want to show you share values. If you are using a thread local from within a thread pool, from when executing tasks inside of a thread pool, then you need to pay a little bit attention. Look at this example here. We have 4 tasks, but only 2 threads, right? So the first and the fourth task are executed by thread 1, and the second and the third task are executed by thread 2. And that, of course, means that the values that are stored inside of this thread local here, when these tasks are executed, will not be completely unique for each task, but only unique for each thread. And so you have to keep that in mind, that in case when executing a task that you are storing a thread local value in here, make sure that you are not reusing a value stored by another thread earlier. And in case you design your code so that it still does, just make sure that that is valid. Okay, so it is perfectly possible to share values between tasks because they're executed by the same thread, but you need to think about it when you design your code. Finally, I just want to show you a special class which is called inheritable thread local. And an inheritable thread local is a thread local which can share its values with child threads created by a parent thread. And to illustrate that, I have created an example here on the left, which first creates a normal thread local, and then it creates an inheritable thread local. And then it creates a new thread here, thread 1. And thread 1 then sets a value inside the thread local and inside the inheritable thread local, and then prints these values out. Now thread 1 creates a child thread, and this child thread also gets the value out of the thread local and inheritable thread local. And what you will see here is that the normal thread local will return null because this thread here is not the same thread that set the value up here. But in the case of the inheritable thread local, you will see that it actually gets the value out because the value is inherited by this child thread because it was set by its parent thread. And the way you find out what is a child thread and a parent thread is simply that the thread here that creates another thread then is the parent of the thread it creates. So this is the child thread, and because this other thread here created it, that's the parent thread. And then this child thread is then started, and thread 1 is started, and we can then see the result. And then we create here another thread here. This is just a normal thread 2. As you can see, thread 2 does not inherit any of the values set by thread 1, and thus you will get 2 nulls out here. Let's run this example here and see that my claims are true. First, we have thread 1, which can get both of the values out that it has inserted into the thread local and the inheritable thread local. Then we have the child thread, which cannot see the value inserted into the thread local, but can see the value inserted into the inheritable thread local. And then you have thread 2 here, which cannot see any of the values because they were set by other threads. That's all for this video about the Java thread local class. Remember to check out the description below the video for a link to a textual version of this tutorial, as well as other related tutorials, for instance, my Java concurrency video playlist. And if you like this video, hit the like button. And if you want to see more videos like this, subscribe to my channel. Thank you for watching. Race conditions is a situation where 2 or more threads access the same variables or data in a way where the final result stored in the variable depends on how thread access to the variable